Welcome you all in this course of Internal Combustion Engine, Fuel and Lubrication. My name is Amit Kumar Tripathi. I am working as an assistant professor in the Department of Mechanical Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. So, this course IC Engine, Fuel and Lubrication is generally taught in taught to mechanical third year student, and as its name suggests, internal combustion engine. So, I will discuss about the internal combustion engine and the fuels which is mainly used in internal combustion engine and the lubrication associated with internal combustion engine. So, in this lecture, I will deal with the basic introduction to the internal combustion engine. So, the introduction to internal combustion engine. As we all know that in case of internal combustion engine, low grade energy heat is converted into high grade energy, and the energy conversion plays a very important role in case of the internal combustion engine. And if we look on the history of internal combustion engine, so we found that the energy conversion, the main feature of our today's civilization, is different from all other civilization, is the wide use of mechanical power. At one point of time, the primary source of power was man's muscle power. After that, people started using animals, winds, running stream. So, the great changes occurs in this field when man learns the concept of energy conversion, and the machine which does this job of energy conversion is known as engine. So, an engine is a device which transforms one form of energy, into another form is known as engine. Most of the engine converts thermal energy into mechanical work, so that they are also called heat engine. So, heat engine is a device which transforms the chemical energy of a fuel into thermal energy, and this thermal energy utilized to perform useful mechanical work. So, thus the thermal energy is converted into mechanical energy in case of the heat engine. So, further heat engine can be classified into two main categories, that is first is internal combustion engine and second is the external combustion engine. So, as name of the subject suggests, our focus is on the internal combustion engine. So, we will look on the internal combustion engine, which is further classified as reciprocating engine, Wankel engine and rotary gas turbine. But again, our focus is on the reciprocating engine, because we all know that our transportation system is work on the reciprocating internal combustion engine. And this reciprocating internal combustion engine is further classified into two categories. First is compression ignition engine and second is spark ignition engine, and which is further classified as two-stroke engine and four-stroke engine. There are so many other classification of the internal combustion engine, but mainly which we will discuss in this subject, in this curriculum, internal combustion engine is reciprocating type internal combustion engine, compression ignition engine and spark ignition engine, which is further classified two-stroke compression ignition, four-stroke compression engine, two-stroke SI engine and four-stroke SI engine. So, internal IC engine have many applications, like it is used in road vehicles like scooter, motorcycle, buses, so many other transportation system, aircraft, motorboats, and in case of some small engines such as lawn mowers, chainsaws and portable engine generators. So, these are the basically some important application of the internal combustion engine. There are a lot of another application also of internal combustion engine. So, question come, what is the need or importance of this subject, internal combustion engine? So, as we all know that the IC engine are the main transport mover in today's society, and for any country the economy plays a very important role, and this transportation system plays a very important role to increase the economy of any country. So, the IC engine, or you can say the transportation system, is important for any country, for any economy. So, if we look on some figures, we found that approximately 7.7 billion people are living on this planet, and approximately 1.015 billion vehicles are present on this planet. So, we can roughly say that every 7th person on this earth having vehicle. So, you can understand the importance of the vehicle in the life of human being. So, that much amount of vehicle are present on this earth. So, if we make the circle around the earth, approximately 125 circle can be made around the earth by using these vehicles. As far as Delhi is concerned, the human population growth rate in 2019-20 is approximately 20%, 24%, and the vehicle growth rate is approximately 100%. From the previous year, the vehicle growth rate is 100% in case of 2019 and 20. So, you can understand the importance or importance of vehicle in the life of the human being. So, that much amount of that much number of vehicles are present on this earth. So, you can also understand that the amount of fuel consumed by these vehicles are also very large. So, if any engineer, any scientist claim that he can save the fuel, or he can increase the efficiency by only 1%, so you can understand that very large amount of fuel can be saved, and that person, that scientist will be the richest person on this earth. As far as efficiency is concerned, in case of two-stroke engine, roughly efficiency is in the range of 10 to 12%, or maybe it may be 13%, maximum 14%. So, for example, if the efficiency of two-stroke engine is 11%, so you can understand that remaining 89% heat is liberated into the atmosphere, which is not in use. So, in case of internal, it means if the efficiency of the two-stroke engine is 11%, it means if we are supplying 100 kilojoule heat to the engine, only 11 kilojoule heat is converted into mechanical work, and remaining 89 kilojoule heat is transferred to the atmosphere through different sources, through silencer, through the exhaust gases. So, you can understand that large amount of energy is wasted to the atmosphere, and that created pollution and other effect on the human being and environment. So, in this case, if any engineer, any scientist claim that he can increase efficiency even by 1%, so you can understand how much amount of fuel can be saved. If I am talking about the four-stroke engine, in case of four-stroke engine, the thermal energy of four-stroke engine is in the range of 29 to 30%, 35% maximum. So, you can understand that if we assume that the thermal efficiency of four-stroke engine is 30%, so the remaining 70% is liberated into the atmosphere. So, if we supply 100 kilojoule heat into the engine, then only 30 kilojoule heat is converted into the mechanical work, useful work. We got this useful work from this 30 kilojoule heat, and remaining 70 kilojoule heat is transferred into the atmosphere. So, the energy conversion efficiency is plays a very important role. So, the conversion efficiency, if any engineer scientist claim that he can increase that, you can understand the conversion efficiency in case of internal combustion engine or any engine, any heat engine, because we know that the low grade energy heat cannot be 100% converted into high grade energy work. So, the conversion efficiency plays a very important role. So, if we looked on the different part of the internal combustion engine, some of the different important part of internal combustion engine are cylinder, cylinder head, piston, piston rings, connecting rod, crank, crankshaft, engine bearing, flywheel, governor and valve. There are so many other components, but mainly these are the basic component of the internal combustion engine. And you can see from this diagram, this is the basic schematic diagram of the internal combustion engine. You can see that it is the spark plug, exhaust valve, inlet valve, cylinder, piston rod, crankshaft, wheel and piston. You can see this is piston. So, this is the basic nomenclature of internal combustion engine. Material used for the engine parts, for example, cylinder head is made of cast iron, cast aluminum. Cylinder liner is also made of cast steel, cast iron and aluminum alloys. Engine block is also made of cast iron, cast aluminum or aluminum alloy, welded steel. Piston is also made of cast iron, cast steel and aluminum alloys. Piston rings is made of forged steel or case hardened steel, because this piston ring reciprocate inside the cylinder and there may be chances of the wear out to the piston ring. So, it is case hardened. So, the wear rate is decreases. Connecting rod is also made of forged steel, aluminum alloy, piston rings, cast iron, connecting rod and bearing, bronze wheel. Main bearing is white metal steel block. Crankshaft is made of forged steel, crankshaft is also made of forged steel, cast iron and cast steel. Timing gears, cast iron, fiber steel and forging. Push rod is made of forged steel. Engine valve, forged steel and alloys. Valve spring, carbon spring steel. Manifold, cast iron, cast aluminum alloy. Crankcase, cast iron, welded steel. Flywheel is made of cast iron. Studs and bowl of carbon steel and gasket is made of cork, copper and asbestos. So, you can see that mainly the component of internal combustion engine is mainly the material used is cast iron, and the cast iron aluminum alloy is used in case of the internal combustion engine. So, if we look on the IC engine thermodynamic term, so you can see from here it is inlet valve, exhaust valve, top dead center, bottom dead center. TDC is top dead center. It is the point or location where piston, the uppermost position of the piston is known as top dead center and the lowermost position of the piston is known as bottom dead center. And the TDC to BDC piston motion is called the stroke of the piston. If the piston moves from bottom dead center to top dead center or top dead center to bottom dead center, it is known as the stroke of the piston. And the distance covered by the piston is called the stroke length, and this length, this distance is known as stroke length and is generally represented by capital L. And the volume covered for one stroke is called the stroke volume. So, the volume from TDC to BDC, volume covered from TDC to BDC is known as stroke volume. Generally, it is represented by V suffix S. And you can see from here the volume covered from TDC to BDC is the stroke volume, and the volume from the top dead center to the cylinder head, this volume is known as clearance volume. So, the ratio of clearance volume Vc to the stroke volume Vf is known as the clearance ratio. It is generally represented by capital C, and the volume at the beginning of the compression is V1, you can see from here. So, basically the piston will move from top dead center to bottom dead center during suction stroke, and then inlet valve will be closed, exhaust valve is already closed. So during compression stroke, piston will move from bottom dead center to top dead center, and at the beginning of the compression stroke, means piston is at the bottom dead center. So the volume at the beginning of the compression stroke, it will be V1 will be equal to Vs, total volume will be equal to Vs plus Vc, and the volume at the end of the compression stroke, that is piston reaches at the top dead center, then V2, the volume at the end of the compression stroke, V2 will be equal to Vc. So the ratio of V1 by V2 is known as compression ratio. It is generally represented by small r. And we already know that V1 is equal to R is equal to V1 by V2, and V1 is equal to Vc plus Vs upon Vc. So R will be equal to 1 plus Vs upon Vc. So first thermodynamic term is the clearance ratio, which is the ratio of clearance volume to the stroke volume. Second thermodynamic term we have defined today is the compression ratio, which is the ratio of volume at the beginning of the compression to the volume at the end of the compression. So after putting the values of V1 and V2, we find that Vc plus Vs upon Vc, or we can also say that R is equal to 1 plus Vs upon Vc. So moving to the different cycle used in case of the internal combustion engine are Otto cycle, which is generally used in the petrol engines, diesel cycle, which also generally which is used in the diesel engine, and the dual cycle, which is used in the diesel engine. So we will discuss in detail the importance of these cycle and what is the thermal efficiency of these cycles in detail. So talking about the Otto cycle, in case of the basic difference between these cycles is in the heat addition. So in case of the Otto cycle, heat addition takes place at constant volume. Remaining properties of gases like pressure increases, temperature increases, and entropy increases. And in case of the diesel cycle, heat addition takes place at constant pressure, volume increases, temperature increases, and entropy increases. And in case of the dual cycle, heat addition first takes place at constant volume, then heat addition takes place at constant pressure, and remaining properties like pressure, temperature, and entropy increases. So you can see from here the basic difference between these cycle is in the heat addition process. So in case of Otto cycle, constant pressure heat addition, constant volume heat addition. In case of diesel cycle, constant pressure heat addition. In case of dual cycle, first heat addition takes place at constant volume, then heat addition takes place at constant pressure. So if we move on the working of the Otto cycle, which is also known as constant volume cycle, because the heat addition takes place at constant volume. So the other name of the Otto cycle, you can also say that it is constant volume cycle or Otto cycle. So you can see from here PB and TF diagram. First, if we started from compression stroke. So if piston, you can see from here, top dead center, bottom dead center, you can imagine it is piston. So 1 and 2. If piston will move from bottom dead center to top dead center during compression stroke, then the gases or mixture of fuel and air will start compressing, and the pressure and temperature of these gases will increase. And you also know that if the piston will move in upward direction, the volume of these gases will decrease. So you can see this process 1 to 2, that is the compression process. So during compression stroke, piston will move from bottom dead center to top dead center, and the gases will start compressing from 1 to 2. So, from here you can see that pressure increases, volume decreases, and when the piston will reach on the top dead center, then at that time, if for example if it is a spark ignition engine, then at this position when the piston reaches a top dead center, a spark plug produces a spark inside the combustion chamber and the fuel start ignited, and the whole pressure and temperature due to the combustion of fuel inside the combustion chamber increases rapidly. So, at constant volume, pressure increases to a very high value. So, 0.3 is the maximum pressure condition, and after that when pressure increases inside the combustion chamber, this pressure will act on the piston top and it pushes down to the piston, and piston will start moving in the downward direction from top dead center to bottom dead center, and this stroke is known as the power stroke or expansion stroke. In this stroke, the gases start expanding because the volume increases. If piston will move in the downward direction, then the gases will expand, and volume increases, gases will expand, and the pressure decreases. So, the pressure act on the top of the piston, due to which this piston is connected to the connecting rod is connected to the crank, and crank will start moving. So, we will get power and the vehicle will move in the forward direction. So, you can see process 1 to 2 is the compression process, process 2 to 3 is the constant volume heat addition process, process 3 to 4 is the expansion process. In this process, volume increases, pressure decreases, and it is also known as power stroke. And after that, when piston will reach at the bottom dead center, the exhaust gases will be produced, and now these gases are not in, these gases cannot be used because the combustion is already completed. So, this exhaust gases will go out from the exhaust valve to the atmosphere. So, in this case, if we open the exhaust valve, the exhaust gases will automatically go out to the atmosphere because the pressure of the exhaust gases is very high. Generally, the pressure of the exhaust gases is 3 to 4 times of the atmospheric pressure. So, the pressure of exhaust gases is 3 atmosphere to 4 atmosphere. So, you can understand that the pressure is 3 to 4 times more than the atmospheric pressure. So, if we open the exhaust valve, the exhaust gases automatically, due to the pressure difference, it will go out to the atmosphere. So, generally it is known as the heat rejection process, because this exhaust gas is associated with the heat, and if these exhaust gases will go out to the atmosphere, that the heat will be transferred from the system to the surrounding. So, it is also known as heat rejection process. This heat rejection takes place at constant volume. So, you can see process 4 to 1 is the constant volume heat rejection process. If we look on the TF diagram, you can see from here that process 1 to 2 is the isentropic compression process. On the TF diagram, 1 to 2 is the isentropic compression process. 1 to 2 is the isentropic compression process. So, it will be vertically straight line, and we know that due to compression, entropy of the gases increases. So, the direction will be in upward direction. Process 1 to 2 is the isentropic compression. Process 2 to 3 is the constant volume heat addition process, and we know that in the TF diagram, constant volume process is like this. So, due to heat addition, pressure and temperature increases. So, the direction of the process will be from 2 to 3, and process 3 to 4 is the isentropic expansion process. So, heat is rejected into the process 3 to 4. So, it will be the isentropic expansion process, and process 4 to 1 is the constant volume heat rejection process. And we know that constant volume process on the TF diagram is like this. So, heat is rejected, so the temperature is decreases, so direction will be like this. So, this is all about the PV and TF diagram of the Otto cycle, and we will continue the derivations and the thermal efficiency of the Otto cycle in next lecture. Thank you very much.